Would you like an introduction or?
Okay, so yeah, I don't know what's the
Well,
protocol.
it's my pleasure to welcome back Vadim Kaimanovich, who will give part 3 of his mini course on. Oh, I forgot the title of your mini course.
The title was Self-similarity in random walks.
So go ahead.
Maybe the other way around. Okay, so let me remind you what we have done so far. So we are considering a countable group G endowed with a probability measure mu, so it's like a Riemannian structure, and we're looking at the properties of the associated Markov chain, of the associated random walks. And there is a qualitative invariant of this random walk, which is the Poisson boundary. So that's an object which depends both on the group and on the measure. And I remind you, it is defined in the measure category. So that's a space with a certain measure endowed with an action of our group. And then there were two quantitative invariants. There was the rate of escape, showing how fast our random walk goes to infinity with respect to a given left invariant metric, for instance, the word metric corresponding to a certain generating set. And finally, the third invariant, which was also numerical, was the asymptotic entropy, which in a sense is analogous to the rate of escape, but it in a sense measures how fast our random walk goes to infinity in the informational sense. If we measure information by entropy. And last time we discussed how these quantities are related to algebraic or analytic properties of the group. In particular, we discussed the link with amenability of the underlying group of the group G. And now I'm going to return a little bit. I do these returns every now and then. I'm going to say a couple of words more about the relationship between these three invariants, because so far what we did, we started from the random walk, and then one way of looking at it was to look at the Poisson boundary. And another way was by looking at these invariants. However, it turns out that these invariants can also be determined just by looking at the boundary of the group, and that's what I'm going to describe now. So let me begin the geometrical notion of the Boosaman cocycle and Boosaman compactification.
So when you say by these are invariants, you mean invariants by the obvious morphism between groups that.
Well, I will be actually talking about these structural properties. No, here I just use fancy word invariant. Well, I could have said just numerical characteristics. Okay, so Boosaman cocycle and Boosaman compactification. Okay, that's supposed to be L and E, and Boosaman compactification. So what is this? Suppose we are given a metric space, and then we can assign to any point of this space a cocycle, in other words, a function which depends on two arguments from this space and satisfies the cocycle identity. So this function is just the, let me denote it by beta z of x, y. And this is actually a trivial cocycle. It's cohomologous to 0. So that's just the difference between the distances from y to z and x to z. Okay, now there is actually a way to obtain a compactification of our metric space by using this co-cycle, which is called Boosaman complexification, and it consists in the following. By using these distance, or rather differences between distances, one can embed the space X into the space of functions on itself. And then we will consider this by assigning, so if we have a point, then what's the function associated with this point? It's just a distance function, the distance to this point. And now I will projectivize the space of functions by considering all the functions only up to additive constant. Okay, and then it will provide an embedding of our metric space into the space of functions on itself, and there one can further take the that's a compact space in the topology of pointwise convergence, and there one can take the pointwise not pointwise, one can take the closure of our original space X. So this will be a compactification. This is what's called Boosaman compactification. Okay. So now what's the meaning of this compactification? A sequence of points Zn converges to a point at infinity, let's say gamma, if and only if for any pair of points y and x, the distances between the difference between the distance from y to the n and x to the n converges. And this will be precisely the limiting Boosaman cocycle. So this will be the limit cocycle corresponding to our point gamma. That's beta gamma of x, y, which could be interpreted as a regularization of the following expression. So we take the distance between x and not x, so I first take the second argument. So oops, I take the distance between y and gamma, and I subtract the distance between x and gamma. So the standard example when this compactification is very well known, coincides with the geometrical compactification, is the situation when we have, let's say, a hyperbolic space, or in the simplest situation, just a tree. So in this case, if we have a boundary point gamma, then if we take 2 points inside, x and y, then we know that the geodesics issued from x to this point gamma, they actually converge at infinity, and this is why the difference between these, the distances of these 2 points x and y to the point gamma makes sense. So in this case, the Boosaman compactification coincides with the geometrical hyperbolic compactification. Okay, so now how does it related to random walks? So suppose that we have now our random walk, and suppose that we know that almost every sample path converges to a limit point from the boundary of the Boosaman compactification. And then on this boundary, I have the resulting heating measure or harmonic measure. Then let's look, let's see how one can express this rate of escape in terms of the heating measure and the Boosaman cocycle. So my position at time n is the product of n increments of random walk. Okay, and now I want to compare how this length changes when I add one more increment. And the trick here is to add this increment not at the end, not to add the increment with the index n plus 1, but instead to add an increment at the beginning. Since we're interested in the integrals, then the result will be the same. Okay, so let's look then at the distance between the product of, okay, here h0, h1, and so on, hn. So here that's n plus 1 increments minus the length of the product of just n increments. So in terms of the distance to which this norm I have written corresponds, so that's what? That's the distance from h naught minus 1 to the product of the remaining n increments, and that's precisely our position at time n. Okay, and the second term is precisely the distance from the origin, from the identity of the group to this point Gn. And this distance, by the definition of complexification, converges precisely to the Boosaman cocycle at the point G infinity, evaluated at the pair of points E, the identity of the group, and the increment which I have just added. Okay, so the moral is that if we add the increments at the end, then the distance will be increasing in an irregular way. However, if we add increments at the beginning, then the influence of this change on the global distance will be actually quite well controlled. So this increment actually converges. And therefore, the average increment of the distance when I add one more increment of my random walk will be the following. I just have to average over all possible increments here, h naught. So let me write the integral formula. So first I have to average with all the increments that I add, mu of g. And then here I have to pass to the limit as gn goes to infinity, and then therefore I have to integrate with respect to the resulting distribution with respect to the harmonic measure on the boundary. So here I will have the integral of the Boosaman cocycle evaluated at the pair of points E and G minus 1, and all this integrated with respect to the heating measure on the Boosaman boundary. This observation was first made by Furstenberg in a slightly different form, because he was talking about products of matrices, and therefore he was talking about logarithms of norms. And actually, independently, at more or less the same time, it was also made by Hasminsky, a probabilist. Okay, so this gives us, therefore, a way to express the rate of escape in terms of the distribution of the boundary of the Boosaman complexification. Provided that the random walk converges in this Boosaman complexification. So that's the case, for instance, when we're talking about free groups. In general, our random walks need not converge in the Boosaman complexification, because the Boosaman complexification is too fine. It's finer, for instance, than the hyperbolic complexification. However, in this situation, there are tricks which allow one to bypass this difficulty. Well, instead of the heating measure, one has to consider a certain measure which is maybe not as nice, but still will play, and not as explicit, but still will play. Okay, so that was about expressing of the rate of escape in terms of boundary measure. And in a similar way, one can also express the asymptotic entropy. And in this case, I don't need Boosaman complexification. It can be done directly in terms of the Poisson boundary. So here one uses the same idea of adding one increment at the beginning instead of the end. So I remind you that the asymptotic entropy tells us how fast the n-fold convolution of our measure decay along sample paths of our random walk. And now in the same way as with the distance, I will look at the following ratio. I will look at the probability to be at time n+1 at the product of n+1 increments. H0, H1, and so on, Hn, divided by the probability to be in n steps at the product of n increments between 1 and n. Okay, and here, what is this? This is, in other words, the n+1 fold convolution shifted by this first increment. So in other words, that's the ratio of H0 minus 1 shifting the convolution with the index n+1 divided by the just n-fold convolution unshifted and evaluated at the same point, Gn. So that's the product of our n increments. Okay, and then this ratio actually converges to the ratio, or rather I should say to the Radon-Nikodym derivative of the harmonic measures on the Poisson boundary. So here I will have the shifted measure, H0 minus 1 u over du, evaluated again at the point G infinity, but now G infinity is a point from the Poisson boundary. And then, therefore, since here, when I add my increments at the beginning instead of the end, the limit exists, then I just have to integrate these limiting values. And therefore, it gives me an analogous formula for the asymptotic entropy, which therefore is equal to what? So I, as before, I have to average with respect to the increments, u of g. And then what do I integrate? So G now plays the role of H0. That's a mu distributed increment. And then I have to integrate the logarithm of this Radon-Nikodym derivative. And here I have to put minus because this will be the exponential rate of decay, and therefore for finding entropy, which is positive, I have to invert the sign. So this formula actually quite similar to formulas which appear in symbolic dynamics, because what we have here under the integration sign, in a sense, can be considered as an analog of the Gibbs cocycle. Because what is this? That's actually the Radon-Nikodym cocycle. And Gibbs cocycle is nothing else than the Radon-Nikodym cocycle of the Gibbs measure corresponding to a given Gibbs potential. So that's analog of Gibbs or cycle. Okay, so that's the end of the discussion about the Poisson boundary and the two numerical characteristics of our random walk, the rate of escape and the asymptotic entropy. And now, before finally starting to discuss self-similarity, I have to say a couple of words about what happens with random walks and with these numerical characteristics and natural structure maps, which we can apply to random walks, because renormalization is about what happens with respect to certain transformations, right? And now I have to discuss what kind of transformations we may expect when talking about random walks on groups.
So, but you have just prepared these formulas for future, or just it is these formulas?
These formulas, well, actually, for a distant future, I think it's useful to mention that, because our current knowledge of self-similarity for random walks is that we can only use it in the case when the boundary is trivial, and therefore all these invariants have to be zero. However, I do believe that it would also make sense to ask about possible self-similarity phenomena in the non-trivial, when these invariants are non-zero. Okay, so structure, let's call it structure maps. Okay, so what happens with random walks with respect to natural transformations of groups? So what are these natural transformations? So first of all, let's consider quotient groups. Namely, I have a group, I have a normal subgroup, and then I consider the quotient map, which sends my group to the quotient group. In this situation, the Poisson boundary behaves very nicely. It behaves functorially. Namely, the Poisson boundary will also be the Poisson boundary of the quotient group will be, or rather of the quotient random walk, will be a quotient of the original Poisson boundary. Okay, let me write the formula. So now I have a homomorphism of my group G onto its quotient group G prime, and then since I have a measure on my group, then it projects onto a measure on the quotient group mu prime. Okay, and then it happens that the Poisson boundary of the quotient group endowed with the quotient measure is actually the quotient of the original Poisson boundary by the same normal subgroup. So what do I mean by this quotienting? I remind you that the Poisson boundary is a measure G space, and therefore this normal subgroup H acts on the bigger Poisson boundary. And then one can look at the space of ergodic components of this action. So that's the natural notion of quotienting by a normal subgroup in ergodic theory. And it turns out that the resulting space of ergodic components of the action of the normal subgroup is precisely the Poisson boundary of the quotient group. So it shows that the Poisson boundary actually is functorial. Unlike other boundaries which are sometimes considered, for instance, in the topological category, one considers Martin boundary, which is very popular among probabilists, but the Martin boundary is not functorial. In a sense, it's more artificial object than this Poisson boundary. Okay, then that was quotient groups. Then what happens when we are dealing with subgroups? So now my group G prime will be a subgroup of G. As always, I'm talking about random walk. So I have a random walk on the group G. I have a probability measure on G. And now somehow I want to obtain a probability measure on G prime, or rather I want to obtain a random walk on this quotient group. And one can do it in a very natural way, namely, here one has to require that this subgroup G prime is recurrent. G prime is recurrent for the original random walk. What does it mean? It means that our random walk on the bigger group will hit this smaller subgroup infinitely often. And then we can just consider the trace of our original random walk on this smaller subgroup. So for instance, one can look at the following example. Let's say G is the square lattice and G prime is just Z. Okay, so in this case, we can the random walk on the, okay, so this is supposed to be Z. We can see the random walk on the whole two-dimensional lattice, but then we are just looking at the points or at the moments when it intersects the horizontal line. So that's obviously a Markov chain. And moreover, it is group invariant, so that's actually a random walk. So this recurrence means actually the following. So when we issue our original random walk from the identity of the group G, it means that our random walk eventually has to hit the sub G prime. And then we repeat it again and again by using space homogeneity of the random walk. So in this case, mu prime is the hitting measure on the group G prime. Otherwise, if G prime is not recurrent, it just means that it is too small to be seen in its entirety by the original random walk. And therefore, in this situation, there is actually no reason to expect that the subgroup can have all the information about the original random walk. Okay, so in particular, this recurrence condition is satisfied when a G prime has a finite index. So index of G, okay, so in which order does one write? So the index of G prime in G, let me denote it by D, is finite. In this case, G prime is recurrent, and therefore one obtains the induced random walk, then the behavior at infinity of this induced random walk is actually the same as the behavior at infinity of the original one, because we hit this subgroup infinitely often, and therefore the Poisson boundary is precisely the same. Precisely the same. Now, what can one say about our numerical characteristics, the rate of escape and the asymptotic entropy? Well, first, the rate of escape. That's very simple, because our sample paths on the finite index subgroup are essentially the same. What changes is just the time scale, because obviously we'll be hitting our subgroup not as frequent as we perform our random walk. And therefore, we will be able to go further in the same amount of time if we are measuring the time just on the subgroup. So in the case when G prime has a finite index in G, this rescaling just amounts to multiplication by the index. Why? Because here, if we look at the space of cosets of the group G prime, then there we also perform our random walk. And this random walk on the coset space has natural stationary measure, which is uniformly distributed. Therefore, the frequency of hitting the subgroup G prime will be approximately 1 over the index. And therefore, here we will have to multiply by the index in order to rescale the rate of escape. And the same formula also holds for the asymptotic entropy, more or less for the same reason. Or it can be obtained, for instance, by using the expression for the asymptotic entropy in terms of the Radon-Nikodym cocycle on the Poisson boundary. So that's actually where I need that formula about which Misha asked. Okay, now maybe one more structural map, which is, well, it's not really a structural map, but it is natural in this context. To look at what happens for product groups. So suppose, for simplicity, that we just take the product of our group G by itself. Okay, so here, this probabilistically corresponds to considering now, instead of just one random walk, considering two random walks. One on one copy of the group G, the other one on the other copy of the group G, and then one can ask about the interrelation between these two random walks. In terms of the transition probabilities, in terms of the step distributions of these random walks, so now one can look on this product group at various measures mu, and if we are talking about functorial properties, then okay, let me denote it by, let's say, mu tilde. So this is a measure on the product of the group by itself. And then, for instance, one can look at the situation when we know that the projections of this measure mu tilde on each of these two factors coincide with the same measure. So mu tilde 1 and mu tilde 2, that's the marginals of our joint distribution, mu tilde, are the same measure mu. Okay, but of course, this condition doesn't say a lot about the measure mu tilde, because here we can have a lot of situations. Marginals, of course, don't fully describe the joint distribution. So here for mu tilde, one can take the diagonal measure, and this is this corresponds just to taking two independent, sorry, not two independent, just to taking the same copy of the random walk repeated twice on the first factor and on the second factor. Same random walk. Repeated twice. Or one can take the product of two copies of the measure mu downstairs for mu tilde, and this would correspond to taking two independent random walks. Two independent random walks. And now here one can ask very natural questions. For instance, what if one takes a convex combination of these two measures? Obviously, then what happens? This will be a random walk on the product of our group by itself, such that its marginals will be the same as the random walks on each of the coordinates governed just by the measure mu. And therefore, if we look at the corresponding harmonic measure at the distribution at infinity, mu tilde, so this will be the measure on the product of two copies of my group. Then the marginals of this measure will be the same as the harmonic measure of the random walk governed by the measure mu. However, even if one looks at the simplest situation, simplest non-trivial example, is when our group is just a free group with two generators and the measure mu is uniformly distributed on generators. Even in this case, we actually don't know anything about the properties of the resulting harmonic measure. These properties will be quite interesting because this will be a measure on the square of the boundary such that its marginals are uniform measures. Its marginals are uniform measures. However, if one looks at the conditional measures, so what do we have here? We have two copies. So here we obtain a measure on this square such that the marginals will be uniform measures. However, if we look at the conditional measures on the cross sections, so here the construction is symmetric with respect to the flip map, so that it doesn't matter whether I take horizontal or vertical cross sections. it is completely unclear what would be the properties of these measures. On one hand, here the whole construction is quite homogeneous spatially. So therefore, these measures must enjoy certain homogeneity properties. On the other hand, since here we are taking a non-trivial convex combination, what we obtain will be a certain measure whose entropy will be strictly smaller than the sum of the entropies of two simple random walks. And therefore, the Hausdorff dimensions of these conditional measures must be strictly smaller than the Hausdorff dimension of the boundary. So this will be a certain family of fractal measures on the boundary of the free group, but I don't really know anything about properties of these measures. Okay, so that was the third kind of structural consideration, and now I'm approaching closer and closer self-similar groups. So now I will consider the first class of, let's say, maybe not structural maps, structural considerations. This will be random walks with internal degrees of freedom. So that's abbreviated as RWIDF. And this is actually a very, very natural object, which was rediscovered many times and has many different names. In particular, it's also known under the name of hidden degrees of freedom. It's more physical terminology, or also they're known under the name of semi-Markov chains. This semi here refers to the well-known fact that if one has a Markov chain, for simplicity, on a countable or maybe even on a finite state space, then its quotient is not necessarily a Markov chain. That's very well known. That's actually one way of obtaining non-trivial Gibbs measures, just by gluing together states of a Markov measure. So quotients of Markov chains. Okay, so here, well, I still want to talk about groups. So my state space is still the group G, but to this observed state space, I will add the hidden component, which will be a certain, let's say, finite, for simplicity, set X. Okay, and now this will be my new state space. Okay, let's say G tilde. And here I want to consider random walks, Markov chains, which still satisfy the natural spatial homogeneity conditions. So transition probabilities are equivariant with respect to the group action. Okay, so what does it mean? It means the following. So let me remind you how I defined random, usual random walks on groups. So here, what were the transitions? So if I start from a point G, then I just sample my increment from the step distribution of the random walk, and then I pass to the product GH. So that's an ordinary random walk. And here, what happens, I have 2 points, G and X. And from this pair of points, I have to point to a new point, which is the following. So I have to add an increment on the right to the group coordinate H, and then I also have to switch maybe to another point here, Y. So one should think about all this in the following way. Suppose you are on in a giant multi-story parking. So all the levels of this parking, they look precisely the same, and usually they're quite spatially homogeneous. So that's copies of our group. But here the additional parameter, this hidden degree of freedom, is the number of the level on which you are. And the transition instructions are the following. If you are somewhere in this parking, which looks very homogeneous, so if you look around, it all looks precisely the same. And the instructions will be something like this. So you toss a coin, and then depending on the outcome, you will either go up or down by 1 step. So this will be the transitions on this degrees of freedom. And also you will move left or right within the level coordinates, in terms of level coordinates. So here, in other words, what I do, I sample my increment H from a certain distribution, which now is parameterized by the original and the final positions, the original and the final levels. Okay, so now it means that instead of a single probability measure, now I have a matrix M, which is a matrix of measures. So X and Y belong to our space of degrees of freedom X, and mu XY are measures. And in order to make sure that this is a Markov chain, here what I have to require, I have required that, well, I need a certain Markovian or condition which would guarantee that the resulting matrix is stochastic in a certain sense. And here, this condition is the following. If I take the sum, so these measures are not probability measures, they're sub-probability measures. And if I sum up the total variations, or rather masses, because here all measures are positive, in every row, should be equal to 1. Or in other words, it can be interpreted in the following way. I can just define the numbers Px, Y, which are the masses of these measures, Ux, Y, and then I can consider the whose entries are these Pxy. So this is the transition matrix of the chain on X, on the chain, on the levels of my giant parking. Transition matrix. Sorry. Of the chain on X. Okay, and now I can consider, therefore, my random walks with hidden degrees of freedom in the following way. I perform random walk on the levels prescribed by this transition matrix, whose entries are the masses of these measures mu x, y, but simultaneously with moving from one level to another, I also sample the increment from the corresponding measure mu x, y. And by using this increment, I also move horizontally. I also move along my the level of my garage. Okay, so here then this is not a random walk on a group. Still, it has enough homogeneity so that one can, in the same way as we did for random walks on groups, one can still define the same qualitative and quantitative invariants. One can still define the Poisson boundary. And one can still talk about the asymptotic characteristics, because in what concerns the rate of escape, well, of course, in spite of the presence of these hidden degrees of freedom, one can still measure how fast is your progress in the horizontal direction along the group.
Vadim, so let us look at this model a little bit longer. So it is a new model for, I'm sure, for many people here. So let us see. So this measures mu x, y. It is a measure of the group. It is measures on your group.
That's measures on my group. Yeah. That's
so how you move in the group depends on how you jump in the fibers. That is
okay. So what happens is the following. So suppose I'm at a point gx, right? So I'm at a certain. I know my position, my horizontal position
yes.
within the group, and I know the level on which I am.
Yes.
Okay, then I look at this matrix M. I look at this matrix M. So this is a matrix of sub-probability measures, but the sum of masses in each row is equal to 1.
Yes.
And therefore, I can consider rows of this matrix as probability measures on the product of my group and this space X. Okay, and then for having fixed X, having fixed the level, I sample from this row distribution. And what does it give me? It gives me both y and my increment g. So that's how the transitions of my random walks are organized.
So,
okay, let me maybe write it in more detail here.
Okay,
so I have fixed a point x from which is the level, okay? And then I have the corresponding row, mu x1, mu x2, let's say mu x.
Oops. Everybody lost Vadim?
Yes.
Yes, it was. You see, Vadim, you were not clear enough. So it was the hint that the explanation was not.
Yes. Okay, so which moment was I interrupted?
Well, you started to describe in details this Markov chain. So here is, well, essentially.
Yeah, okay. If we fix our vertical position at that point X from the space of degrees of freedom, then the corresponding horizontal row of the matrix, it's a collection of sub-probability measures, which can actually be considered as a single compound measure on the product of the group and these hidden degrees of freedom. So when I sample from this measure, it gives me both a point from the space X, and that's where I move to vertically, and it gives also me a group element, and this is my increment. Or in other words, that's just one way to describe these random walks. The reason I do it in this way is because I will need it for further discussing the renormalization of random walks. On the other hand, one can use just the original description. So what do we have? Our state space is the product of the group by a certain finite set. And there I consider a Markov chain. So what is Markov chain? I have to assign to every point transition probability from this point, right? And the only requirement which I'm imposing that this assignment should be equivariant with respect to the action of the group. And that's precisely what this random walk with internal degrees of freedom is.
Okay. Okay, thanks. So you started to talk about the boundary of this guy.
Okay, yeah. So now in this situation, for these random walks, so it's not fully spatially homogeneous because of the presence of this additional vertical parameter, but still, since the space of this additional of the values of these parameters finite, our Markov chain is still sufficiently space homogeneous. And therefore, not only one can define the Poisson boundary, which can be done for an arbitrary Markov chain. So here now I will put M as a subscript. This describes our random walk. But one can also define the asymptotic rate of escape. And one can define the asymptotic entropy. Oops, here instead of mu, I have to write M, of course. Which have more or less the same properties as in the case of groups. So here we still have enough homogeneity to apply all these. And then in this situation, we're quite close to renormalization. Namely, now we can look at the following transformation. So we have our state space, which consists of several finitely many copies of our group. So the vertical coordinate is our X and the horizontal coordinate is our group G. Okay, and now I can select just one of these horizontal layers, choose a point X, fix a certain value of this hidden parameter, and look at what we have already done in the case of groups. I can look at the trace of my Markov chain on a recurrent set. I can look at the trace of this random walk with hidden degrees of freedom just on a single layer, just on a single copy of the group. So random walk with these hidden degrees of freedom will induce random walk on the random random walk on our group G, parameterized by a certain measure, which I denote by mu x. So x is the parameter which describes our level. So how does one obtain this induced random walk? So qualitatively, I have already described it. So we are just looking at the trace of our big random walk on one layer, because from kind of natural considerations, it's obvious that we will be returning to this layer again and again. And now it turns out that the transition distribution, the step distribution of this induced random walk actually admits a very nice description in terms of the matrix describing the random walk on this whole building. So one has the following formula. Let me write it and then I will comment it. So what we have to do is the following. So we start from the level x, and then we also have to return to this level x. And then what we have to do, we have to figure out what's the horizontal position, what's how far and where do we move horizontally on this layer when we return to it. Okay, so what I do is the following. So one option is that my jump, the first jump from the level x, actually leads me to the same level. And this will be described just by the transition measure mu xx. Or if not, I will have to move from my level x to elsewhere, to the complement of this level. And this is described by the following matrix obtained from our matrix, from our transition matrix. So here I fix the row, that's where I start from. And the destination, the column, has to be outside of x. Okay, so this is, in other words, the row vector of the point x from which I exclude the diagonal entry. Okay, so it guarantees that now I'm not on the x, on the level of x, so I have to move for a while outside of this point, which will be described in the following way. First by the identity matrix, then I have to take the matrix, which I denote by x bar here. What does it mean? I remove from my matrix M, I remove both the row and the column corresponding to this point x. So this will be a square matrix whose order is one less. It will be d minus 1. And so on. Then, so this will be one step outside of point x. Then in the same way, I may do two steps, which will be described by the square of this matrix and so on. And finally, when I have had enough of being outside of the point x, I have to go back. And this will be described by the matrix of transition, this complement x bar to back to the point x. So this was a row matrix, and this is a column matrix. This is a column matrix. So as a result, actually, I obtain a scalar. But here, since the entries are the probability measure, are the measures on the group G, as a result, I will obtain a measure on the group G. And one can verify, actually, I can write it differently. Simpler. So, and this, what is this? Just I minus M x bar to the power minus 1 m x bar x. So as a result, I will obtain a probability measure. And this is precisely the measure which governs the induced random walk. So actually, this transformation is well known in algebra under the name of the Schur transform. Schur transform. Okay, so the moral is the following. I have started from these, sometimes it's called matrix valued random walk, although it's not exactly right, because still our states are not matrices. They are just pairs, element from the group and this vertical parameter. And then what happens under this transformation with this invariance of the random walk? So the Poisson boundary remains the same. And the rate of escape and the asymptotic entropy rescale in precisely the same way as it happened when I was considering inducing on a subgroup of a finite index. So the rate of escape, therefore, L of G U X, I will have to multiply it by D. For the same reason, because I will be hitting my level only on average one time out of D. And therefore, it means that I will be achieving the same result. I will be at the same distance from the origin, but D times faster, so that the rate of escape will be greater. And the same formula will also hold for the asymptotic entropy. So it shows how the rate of escape and asymptotic entropy rescale under this natural transformation, inducing the random walks on one layer, on a single layer. And that's precisely what I will need when talking about random walks on self-similar groups, which I will do next time. So next time I will define self-similar groups, and I will show how this machinery actually is very nicely adapted to the formalism of self-similar groups.
Great. Thank you.
Questions or comments?
Would you comment maybe on the Poisson boundary of a free product? Is anything possible to
of free product?
Yeah. Any chance for like some kind of fiber structure?
No, for free products of whom?
Of groups.
Okay,
of
what kind of groups?
Well, we have two groups. We have two random walks on each of them, so we take a free product. So we can.
Okay, are they finite or not?
Let's say not necessary.
Okay, so for free products, actually, the situation is quite simple, because there what happens is, well, essentially, how does one write words in free products? Elements in free products, they're syllables, right? So you write a word in one group, then you write a word in another group, and so on and so forth. And that's and this provides a natural boundary structure, actually, because if you can write finite words, then of course you can also write infinite words. So here the situation is actually pretty much the same as for, let's say, free just usual free groups, because, for instance, the free group on two generators is, you can also consider it as a free product of two copies of the group Z.
Yeah.
Right? So here the picture is essentially the same. So the structure at infinity of each of the multipliers doesn't really matter here. The groups, they only serve here as syllables, as the building blocks for these infinite words.
So the Poisson boundaries of these two groups, they don't affect the Poisson boundary of the product?
No, that's precisely the point, because you are not staying long enough in one group in order to see what happens at infinity at this group. Because you see, the moment you start to think about what's your future in this group, you have to move to the next one, and all what you have achieved in the first group, it's forgotten.
So each subgroup is not recurrent in the. So the groups are not recurrent in the free product. Okay.
No. Of course, they're not recurrent. No, unless, well, maybe if you. Well, there is the degenerate case if you take infinite dihedral group, the product of two copies of Z2, but other than that, no. No, because look, if you take Z2 times Z3, then that's, in other words, that's PSL to Z, which in a sense as free as it gets. Well, it has a free group inside and so on.
Do you think it will be possible to count the number of paths of length n of the random walk on this GM and by comparing with the random walk on this G and mu x that you wrote?
Well, okay, so this here you are asking about return probabilities, in other words.
Yes, relates the random walk on the big G times x with the random walk on the G mu x.
Well, so this formula which I have written, this Schur transform, it's, and I presume therefore you can, well, if you are interested in, let's say, paths of length n in the group, then in other words, you are interested in returning to the identity n times, right? So essentially you have to iterate this formula. So maybe one can do some spectral calculations with this formula, but I do not know.
Thank you.
So just I'm wondering about the physical origins of this discussion. So I guess in physics it would be some kind of Ising or Potts model, and somehow they use it in some interesting ways, this kind of random walks. Do you know?
This was, I think, in this way, it was introduced in the 80s, indeed, by people with, so who was that? I think Sass actually wrote one of the first papers on that. Domokos Sass. Yeah, so I think this must have been their motivation.
Maybe next time you could you give us some more precise references, maybe?
Okay, yeah, sure.
Okay, great, thanks.
Questions, comments?
So I have also one question. So I was a little bit confused with this. So the last formula that you wrote about the so the escape rate of the random walk on this for this random walk mu x.
Yes.
So if the stationary measure for the sort of random walk in the x direction is not uniform, I somehow don't see why the L gets multiplied by D and not by so much.
Yes. If not, of course, it has to be multiplied by, or rather divided by the asymptotic frequency of this state. You are absolutely right, but well, there are two reasons why I wrote it this way. One is that I was honestly thinking about the applications, and in these applications, indeed, it is uniform. And second, just to make this picture simple, but you are right, of course. In general, one should write here the asymptotic frequency.
Okay, thank you.
Inverse asymptotic frequency.
Inverse, yes, thank you.
Yeah.
Other questions, comments? If not, let's thank the speaker again.